The hypergeometric distribution is a discrete probability distribution that describes the probability of k successes, random draws for which the object drawn has a specified feature, in n draws without replacement from a finite population of size n that contains exactly k objects with that feature, wherein each draw is either a success or failure. In contrast, the binomial distribution describes the probability of k successes in n draws with replacement. You know, it's a discrete probability distribution. N would represent our fixed number of trials. You'd have some kind of probability, some known probability. The independence is the issue, right? Because it's without replacement, the probability is going to vary from one trial to another, right? So the first example, suppose there are 50 officers, 10 female, 40 male. Suppose 20 of them will be promoted. Let X represent the number of female promotions. We're looking for the number of combinations for 0 female promotions, number of combinations for 20 male promotions over the number of combinations for promotions in general, the 20 promotions. All right. So if we're looking at this from the perspective of, gender bias, then we would want to look at, all the different possibilities. But let's say, for example, that you're a female officer and you've been getting passed up for promotions. You might say, all right, well, what are the chances? And specifically, you notice that there were 20 possible promotions that could have been had, and they all went to male officers. This is an opportunity for you to say, wait a minute, what are the chances of that happening? Figuring it out, and then realizing that it was so highly unlikely that there must have been some sort of outside influence. All right. Now, it could be that the outside influence is that the male officers in this case are all more qualified, but it's also a strong chance that there's some kind of discrimination going on. All right. So that's one case. Another case would be saying, all right, what about just one female officer getting promoted out of the 20? All right. So it's kind of like in the case of binomial expansion, we're increasing the number of successes for one group, all right, until we get to all of them being there, every member of that group. And then we're decreasing until you get to the minimum value that you could have for that group. All right. With the general rule being the hypergeometric distribution. So that is the hypergeometric distribution. Same idea with the Poisson. What you're going to do is make substitutions in for every numerical value here, the 10, the 20, the 40, the 50. Those are all particular to the problem. The I, or X if you want, if you're using it in function form, that's what's going to vary. All right. So how do you put this in your calculator? Well, that's that bracket notation. That's the other type of notation for combinations. All right. So if I wanted to do, and I can just get rid of all this particular distribution, let me make it an f of x. Create a fraction, function, stat, NCR, 10 comma x, close it up, times NCR, 40 comma 20 minus x, close it up, over NCR, 50 comma 20. So that's your hypergeometric graph. Probably haven't seen too many graphs that look like that before. But then from there, you can evaluate. So let's say I wanted to know what the probability was that no females would get promoted. My probability here would be 0.00292. So very, very, very remote, right? I would also look at it on the other hand, from the other perspective and say, what's the probability that they'd all get promoted? Even less likely. All right, well, what's the probability that some of them would get promoted? Let's say 5 of them. About 20%, you know? So you could start playing around with the numbers and get an idea of what's going on in this instance. So we want to make a table to compute all these values. This table it's built off of old school TI-84 stuff, but we have a function built in here now. So what I can do is create a table in Desmos 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And then in Y1, instead of having a Y1 there, type F of X1. And it'll evaluate all the numbers. It'll evaluate all the numbers in X1. And so I would just jot all that information down. All right, so we'd be looking at 0.00292, 0.0279, 0.108, 0.226, 0.280, 0.215, 0.103, 0.0306, 0.00533, 4.905 times 10 to the negative fourth, and 1.799 times 10 to the negative fifth. All right, and so this would be really irrelevant. So this gone, this is X1. This should be F of X1. And this should be F of X1 with a note saying that this is in Desmos. Suppose there are 30 students, 20 male, 10 female, applying to the same college. And this college will only accept 10 students. What's the probability that 5 of them would be male and 5 of them would be female? All right, so let me get my, my distribution again. This is a distribution that's particular to this problem, but we can modify it. And so that's what we're gonna do. There's 30 students in total, and they're gonna accept 10 students. 30 students, they're gonna accept 10 of them. So that's down here. There are 20 male and 10 female. So I would look at that and say, okay, these are my starting values. 20 female, I'm sorry, 20 male, 10 female. All right. The I makes sense because from that 20 of the males, we're going to select I individuals to be part of the set. But then there's only going to be 10 minus I left over for the other group. All right. So it's the same idea, and I'll just jot it down again. We have P of X. I'm going to write it as 20 with an X, 10 minus X over 30, 10. All right. So these are all combinations. So resist the urge, like I had to resist the urge to make fraction bars. All right, so it's 20CX. Right, so for the group of 20 males, we're going to select some number of individuals to get accepted into this college. Out of the individuals that don't get selected that are males, they'll be selected as females. All right. So if let's say only 2 males get selected, that means that there's 8 spots open for females. If all 10 of the spots are males, then there's none left for the females, and so on. All right. So and everything in between. So when I set up my distribution here, it's really simple. It's just a matter of changing this up to match, so save this distribution. 20 would be my first entry. Then 10. Then 10. 30. And 10. All right. So if you change that top entry, that function, then everything beyond that is going to change accordingly. All right. This one goes out to 10. It just so happens I need to go out to 10 anyway. What's the probability that you'll have a 5 and 5 breakdown? So I'm looking for the probability that X is going to be equal to 5. 5 males would imply 5 females. So that would be 0.130 approximately. And I honestly, I don't know where that last example came from. That's not a hypergeometric.